Exploding Rocks is the popular title of the talk. Explosive Eruption of Volcanoes is perhaps more informative title. It's joint work I'm doing with Andrew Fowler, Betty Shoy and William Lee. Andrew is currently at the University of Limerick. He's also at the University of Oxford. He's on back and forth between the two institutions a lot. Betty Shoy is from LMU in Munich. And LMU is Ludwig Maximilians Universität. I had to look that up because I keep forgetting what LMU stands for. And William is also at the University of Limerick. He's just accepted a 10-year position there at Limerick. William's background is physics. Betty is a volcanologist, so she's the owner of this problem. It's a bit like a workshop problem in a way, because there's an experiment and there's a real question or situation that we, William and myself and Andrew, are trying to model. So more about that in a minute. So we're interested in, we're interested in explosive eruptions, and I'll talk about what I mean by that in a minute. There's some lab experiments that Betty has conducted. We would like to explain them mathematically, the mathematical model. The numerical solutions were really my contribution to the work, and then there will be some conclusions at the conclusion. So I'm talking about eruptions, a kind of eruption. Here's a Papua New Guinea Tava erupting. Here's Sakurajima in Japan, the plume coming down from Sakurajima, and then some close-ups of the crater showing explosive events. And I guess you'll be familiar with the idea that eruptions can be slow, effusive flow of magma, perhaps like the Hawaiian ones typically. That's at one end of the spectrum. And at the other end of the spectrum, the very explosive eruptions, hard, bang, 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 rocks flying out, ash plumes like we've seen from Iceland recently, things coming down and landing, exploding, they're called BKBs, bread crust bombs, because the magma sets and the inside is molten, and you don't want to be anywhere near these things. They're the size of a refrigerator or a car, these things that come out, they're big and dangerous. So it's a very explosive kind of eruption. It's named after, that U is deliberate, volcanic eruptions it's called, as a technical term for it, from the island of Volcano, which also lends its name to the island, to the name volcano, I guess, but volcanic eruptions are these very explosive. And it's like the magma is no longer really like a fluid when it erupts. It's being, as it rises, gases come out of solution and drive it forward and break it. And it's become so viscous, it's basically solid rock. So the rock is shattered and broken by gas coming out of solution. That's the idea. That's the geophysics behind it. And to start it off, usually you have the magma is in place, sitting there, waiting, and then the top gets knocked off by something, maybe a landslide, something releases the pressure, and whoom, it just goes like a champagne cork being popped, and out comes the champagne. But as I say, it's not a fluid flow, it seems more like a rock breakage, exploding rock kind of situation, driven by the ex-solution of gas coming out of solution as the magma rises. Shatters the viscous magma, and it's really more of a solid rock behaviour, not a bubbly flow behaviour. And you get a fragment, the geophysicists know there's a fragmentation wave goes down into the magma in that situation. And they're interested in this fragmentation wave, interested in how fast it goes and what's the physics behind it and the mathematical description of it. What's the critical pressure difference to make this happen, for example? They're interested in those questions. Yes, and I mean, when I talked about exploding rocks, the first thing Professor Kwan said was, oh yes, what about that one in Iceland? You know, so here is this, who knows how to say this? Does anyone know how to say this word? It's the name of the volcano in Iceland that's been giving all the trouble lately, right? It's been exploding, and I believe it's explosive eruptions. I put a question mark there because Wikipedia said it was explosive. I don't always trust Wikipedia, so it's not quite. It seems that it is. The ash cloud is quite an inconvenience globally and locally.
Mount St. Helens a good example of this sort of explosive eruption?
Mount St. Helens is exactly a good example, yes. I was told that too. Part of this hill slipped away and then it erupted violently and solid.
I wasn't very far away when it happened, so...
You were close to it?
Not to get the ash clouds yet.
Oh. So, now, does anyone know how to say this? No?
No idea.
I looked on the internet. You can find an Icelandic person listen to a recording of a person saying it. And then I listened to it many times, and I still can't say it properly. Anyway, it is explosive. There's some lovely pictures on the internet of Eyjafjallajökull exploding. So here's Iceland, and here's it's showing up fairly reasonably in here. You can see a plume going down here, and it goes very high into the atmosphere. So it's really had a huge impact on the local population. And there's an aeroplane flying nearby. And you see how small the aeroplane is compared to the size, but it's just a massive eruption. And it's very powerful. Things happen. Here's some of the lightning, you get ionic, there's big voltage differences, big voltages generated, potential differences generated, and you get lightning and you get sparks, and there's molten magma in there as well, so it's all happening, and quite spectacular. There it is in the background, and there's some cloud, and you can see in the foreground there's a local economy, there's an agrarian economy, there's I think it's dairy and beef, so cattle, and the ash clouds affects them. It poisons the cattle, for example. Fluoride, there's fluoride in the ash. They've identified the most poisonous element, which is fluoride. So these people have to get the cattle in, get under cover, clean up, and so they're affected also by this. So it's had a huge impact globally. People are very interested, of course. Here are photographers and volcanologists coming very close, I think dangerously close, to the crater and watching these. You can see explosions are happening. I mean, some of it is molten, yeah, but some of it is not so molten. And again here, I guess some of the shutter speed was slow enough that you could see some of the movement here, some blurring. This cloud is violently moving, and there's molten lava there, and there's lightning in here as well. It's sort of showing up. And it's in an environment of ice and snow, so it's a huge contrast. Amazing, I think quite an amazing location for these. So yes, I think this is an example of exploding rock. With that interest in volcanism and understanding volcanism, Betty Shaw at Munich has conducted some lab experiments. It gets an autoclave, high pressure, pumps in nitrogen gas to 100 atmospheres, 10 MPa, 100 atmospheres. It's about the same pressure as 1 kilometre down under the ocean, under the sea. It's quite high pressure. And then sealed off with 2 diaphragms, metal diaphragms. And then she releases one diaphragm by exploding that with a current. And then the pressure drop naturally explodes the next diaphragm, and the gas rushes out. And in rushing out, it explodes the rock sample in there. And she has a camera, a high-speed camera, and she watches. It's got transparent walls. She watches the side of the rock. The rock is a sample, a volcanic sample, natural sample of volcanic rock. Sometimes at room temperature, sometimes at 800 degrees C, where it's still competent, it still has bond strength, it still has tensile strength. It's still solid, but a little less solid at 800. It begins to melt about 900, 1,000 degrees C. So they've done hot and cold experiments, and she watches the fragmentation. As the gas rushes out, it rips apart the rock. It fragments the rock. If she doesn't glue the rock down, it's a bullet. It takes off, and then it rips apart as well. But it also takes off. It's a gas gun, right? A gas gun. The gas though is in the rock. It's porous. It has permeability, so that the gas can flow in and it can flow out again. So that's the picture. Very high pressure. Bang! Pop the top. Bang! 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 And just in 1 millisecond, it's all over. It's exploded. But with the camera, Suddenly, with camera at 10,000 frames per second, it's possible to see in slow motion the explosion. There's also 3 pressure sensors there, and I'll show you those too. It's pressure, detecting the gas pressure at the bottom, partway up the sample, and then up here near the release point. It's called a shock tube because I guess a shock wave does propagate from here upwards. A rarefaction wave propagates down into here. Pressure drops and the rock explodes. So it's supposed to be a model, a tame, careful model of a volcano, much more controlled, of course. And the rock is clearly solid in this experiment. So Betty was keen to explain what she sees. And what she sees is this. Here we go, it's exploding. So this is the camera. You'll see the explosion happening. And lifting off. Each piece lifts off, a piece lifts off, and then it shatters itself because gas is inside it coming out. So here we go again. A piece lifts off here, here, and here. And it's fragmentation waves going down, and here, and here, and here. And you can see there's a length scale in there. But as each piece goes up, it also breaks apart. So there's a primary fragmentation front and a secondary fragmentation front. Let's see if I can show you that perhaps more carefully. Let's see if we can do something here. So we can go backwards. So you can see here just starting the fragmentation. It's just starting. But then those pieces, as they go up, they also break up further into smaller and smaller pieces. So I guess one of the surprises there was the length scale that's being seen, the layering. That is not going off as powder at the top. It's going off in chunks. And then those chunks break up because they've got gas inside and the gas is rushing out and ripping them apart. That's the picture we have of what's happening anyway. So those are the pictures she had. Betty took those pictures and she then looked frame by frame by frame to see where the first, at the time and the place of the first, the second and the third fragmentation, to graph the speed. So she's shown some graphs, and also to show the cracks and where they are. So X versus T, top, crack, 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 and show them coming. So, that kind of picture. So she's looked at those stills, and she's digitized them basically, and drawn a picture like this, where the height here, 60 centimeters, is the height of the sample, 60 millimeters, sorry, 6 centimeters. Here's the top going off, and then as time goes along here, we can see 2 fragmentation events. She saw 2 at once, and then that bit lifts off, this bit lifts off here, but it breaks in half again. And we can see primary fragmentation events here, here, and here, and the velocity, dx/dt, here's time going on here in milliseconds, and I guess, yeah, we've got 1 millisecond from here to here is 1 millisecond. So it's all happening in 1 millisecond. Speeds are about 100 meters per second. Way below the speed of sound. And as I say, there's a primary fragmentation event and a secondary fragmentation event happening as well, and sometimes these also break up again and again. Depends on how much pressure is used. How fine it breaks is how much pressure is used.
What kind of rock was it?
What kind of rock? That was some of BKB, so it's a bread crust bomb. She used a variety of rocks. They have used. She's not the only one who's done these experiments. The porosity is ranging from pumice right up at 60% porosity, right down to sort of more like andesites, which are down, right down at 0.05.
They all display the same.
You get the same, yeah, layering different speeds and scales, but yeah, they all do it. They all do it, yeah. Actually, it's interesting. When I gave this talk last week in Wellington, there's a guy there who's come to Victoria, a recently appointed professor of volcanology. I was a bit nervous about talking about this with him there, because he knows about volcanoes, and I'm just an applied mathematician, I'm learning about volcanoes. And so he said to me at the end of the talk, actually you can see this layering happen in other much simpler experiments. You take a tube of dust, talcum powder, fill it with talcum powder, and then you pressurize it a little bit. It doesn't need much. He said, a much cheaper experiment. He said, these guys have got too much money, he said. They're using an autoclave and high pressure and high speed cameras. He said, you can do it with talcum powder. And he showed me some papers. And they, same thing, they drop the pressure, let the gas flow out of the talcum powder, and layering happens. That comes out, the talcum powder lifts, not from the top, but partway down, and then of course it breaks up too. So that same thing's even seen with talcum powder, which has almost zero tensile strength. It has some effective because of gravity, because it's held up, it has some effective tensile strength. But, so yeah, it happens in a whole wide range of samples, and even with powder, it happens.
Makes a better talk than exploding rocks. Exploding powder.
Exploding talcum powder. That's serious stuff, exploding talcum powder. You've got to watch that talcum powder. You have it in your bathroom, you think it's safe, but it could explode at any minute. Yeah. So explain this was sort of the challenge, the mathematical challenge, the modelling challenge. Fragmentation wave goes through, and there's a characteristic length scale seen in the experiments. And I guess the previous modelling uses something called shock tube theory, and shock tube theory involves really assuming the magma is not solid. These experiments, it is solid, but they take it to be a liquid or a gas even, a mixture, a gaseous mixture, with a rarefaction wave going into, not really a shock, but a pressure drop propagating into this mixture, a gaseous mixture. And that's the theory behind this, and the overpressure in the gas bubbles can burst and pulverise the rock. That model has a number of drawbacks, but I guess the main one is it doesn't predict a length scale. It says it'll pulverise right from the top all the way down, no length scale. It assumes it's liquid or gaseous. It's a shock wave, which is really a gas assumption. And it's not, I mean, there's solid rock there too. There's an interaction between rock and gas, but that's ignored. So it's taken to be a mixture. It's a continuous process. So, and also across this pressure drop, they then solve the conservation of mass and conservation of momentum, which is good. That's what all we do too, mass and momentum conservation. But it's done in an average sense, just across a jump, just do a jump, make it a shot, do a jump. And then to progress the calculations, you need to assume something about the speed. What's the speed of the fragmentation? It doesn't come from the modelling. You have to, okay, let's assume a constant speed now as well. And then you can get some, the volcanologists have got some results, and they've got, they do say, Koiguchi et al. In 2008 admitted that the physics is not fully understood from this modelling that's been done before. But it actually does surprisingly well. This modelling does very well in terms of matching. Oh, and here's the model. You've got air and you've got a bubbly magma. They're thinking of it being more like liquid. And maybe that's right somewhere else on the spectrum, but not so much good for these lab experiments. And they're thinking of bubbly magma and air, drop the pressure by popping that diaphragm, and then this propagating shock going into, they're thinking of it as being a shock going, it's actually a rarefaction wave, and then just conservation of mass and momentum across the jump, that's all. So it's a nice and simple model, and it has its attractions because of its simplicity. And then assume something about the velocity going down, they assume it's constant, okay, and then they can solve. And they can produce graphs like this one here. The graph is fragmentation threshold. How much pressure do you need to break that rock? Versus the porosity of the rock. How porous is the rock? From 0, no gaps, no gas inside it, to 1, nothing but gas. So and you can see here the dots are samples, so anything up to 80% holes, right down to less than 10% holes here. And of course, the fewer holes you have, the less spaces inside the rock, the harder it is to break it. There's no gas in there hardly, so it's hard to get enough gas in to break it. And then the dots are hot and cold samples. The hot samples are these solid dots. The open symbols are cold samples. Done a whole variety of experiments here. And these different lines that you see going through, they come from shock tube theory, various approaches to shock tube theory. They all do fine. They all give you this sort of behaviour. But that's partly because they're also empirical. They've also said, oh, we can see that pressure goes to infinity as phi goes to 0. So we'll put a 1 over phi in there. So we'll put it in there. And we see it goes to 0 as phi goes to 1. So we'll multiply 1 over phi as 1 minus phi as well. So it's a little bit empirical. But it does fine. The other thing I was very impressed by was their predictions of fragmentation speed versus porosity, initial pressure, sorry. Raise the pressure, here's the fragmentation speed observed, that front going down in there. And these curves come from that conservation of mass momentum across a shock. And they're pretty good. What's happened there? Retrospect notification, that was very unfriendly of it. Actually, that's interesting. Yes, all right, that's what happened. So, here's the data and here's the curves. They're pretty good. And here's a variety of rocks, Wellington and Montserrat, places they got the rock from that they're doing these experiments on, and fits to, as the pressure goes up, the velocity goes up. Okay, those are pretty good. No net scales. So, no net scales, liquid approximations being made, it doesn't seem much like a liquid, a solid rock. And constant velocity had to be assumed to make progress. Okay. So it's pretty empirical. Okay. So our task was to just checking the time. Our task was to try and, I think, produce a more physically based model and to capture the length scale that's seen in experiments. So, yes, that's right. When I gave this talk at Vic, I was conscious that people didn't know what I meant by mathematical modelling. They'd had a talk 1 month ago from the same group, a math group, called Model Theory, which is quite different, it's pure mathematics, right? And I've just shown this picture here. It was drawn by a friend of my daughter's at school. They were in their last year at school, so they studied some calculus, right? And the girls have been talking about what their fathers did, what work their fathers did. And my daughter said, well, my dad models differential equations, or models with differential equations. So I was very impressed that Anna, who knew me, and at this school they must address their adults, they can't address adults by their first name. And when I met Anna, I said, I'm Mark, call me Mark. So her compromise was to call me Mr. Mark. So there we are, Mr. Mark. Mr. Mark, and she drew this picture for me, which is inspired by her conversations with my daughter. Mr. Mark modelling differential equations. So she's put me in a dress, but she's also put some derivatives and some differential equations in there. I was very impressed that she got it right. That's what I do. I don't wear the dress, but I'm very interested in the equations on the dress.
You know the catwalk.
She's got me posing like this. That was a bit mean, and she's given me hairy legs. So it's this picture is actually framed on my office wall, so I'm very proud of it. Yes. But here's what mathematical modelling really is. First of all, we think about what's the problem, what's going on, and we have to go back to 1956, 1962. A guy called Biot, a Frenchman, I guess. He wrote down some equations, and these equations were about gas flow through an elastic porous medium. So very careful, fundamental equations about gas flow through a deformable elastic porous medium. And what's the deformation and what's the flow? So it's Darcy's equations, but stress and strain in there as well. Solid mechanics in there as well. And I'll show you those equations. Conservation of mass, yes. And momentum, yes. And energy, adiabatic assumption that in the time of that happening, there's no heat transfer. Very reasonable assumption. So this is what they do in the shock tube theory too, but this detail of not assuming a shock is the difference, really. We're also a bit careful about Darcy's law, or what the drag is. We realised, I guess, that drag between the rock and the gas was very important. It rips it apart, so it's dragging it apart. And it's also turbulent flow, so we've gone, instead of Darcy's law, we've gone with Forsheimer equation, which is a correction for turbulence. Got a quadratic dependence on speed. So we make pressure drop and velocity, but quadratic dependence is the idea. So then the stress-strain relationships are very important, because in this model we want to say, when does it break? Okay, the gas is pouring out, stress is going up, critical strain, breaks. That's the idea. And yeah, at critical stress, we break the rock. So here's what the equations look like. I I just want to convince you that we have looked at conservation of momentum and energy, mass, momentum and energy. That picture there is Karinsky volcano in Kamchatka, and that's explosive and eruption as well. So we've got an equation here, which is a momentum and conservation equation. You can see we've got a acceleration term here. So it's just, well, momentum conservation, or if you like, Newton's law, force of mass times acceleration. And so we've got stress term here. We've got A and D and F, which are explained down here. I'll get to them in a minute. So we've got the momentum conservation for the rock. So W is displacement of the rock. We've got the momentum equation for the gas. V is the gas velocity. And the pressure gradient driving that. And we've got A and D appearing here. And these are A and D interactions between the gas and the rock. A is and we've got a stress-strain relationship, that the stress is relative to strain in the usual way with an elastic constant. And the pressure is in there as well, of course. So the added mass term is the idea is that it's an inertial term, really. That when you flow gas past an obstacle, there's an impact effect. You think of little gas particles hitting. So the difference in velocities, differences in acceleration, lead to an added mass effect. Or there's an approximation to an inertial thing in there. And I guess the one that you think of first up would be this interfacial drag, Darcy or Forsheimer, in fact. So the velocity difference leads to quadratic velocity difference leads to a drag. Difference between the velocities of the rock and the velocities of the gas leads to a drag term, which affects both momentum equations, equal and opposite ways. So added mass and drag terms. One's inertial and one's viscous. This is all from Bio's papers in 1956, 1964. Modified a little bit to our situation. So then we've got mass conservation for the gas and an equation of state, adiabatic situation here. It's very important that we had wall friction for the glue in here. The F is a wall friction term for the glue. Without the wall friction, we had difficulty with the model. It wasn't giving us a length scale. It was giving the whole thing breaking at the bottom, always, until we put glue in. And of course, experimentally, if you don't put the glue in, it lifts off first. So it was very important to put this glue to a force, and sort of a net displacement dependent force. And the idea is that the glue holds the side of the rock. You pull that glue and you get a little bit of displacement, and the glue pulls back again. So the displacement creates a force. Without that force, without that simple term in there, the model did not predict what the experiment showed. It predicted maximum stress at the bottom, off it goes. End of story. Almost end of story. Which is true if you don't glue the sample down, but we needed to explain what happens with glue. And so that was the magic. That was the magic term, wall friction term.
So is that for the experiment?
Yes. Yes, and I perhaps didn't say it clearly enough. We're modelling the experiment.
Experiment.
Yeah. The volcano is too hard. The experiment is simpler, and we're only trying to model the experiment.
It's a real case. There will be no wall friction.
Yes, there is wall friction in the real case. The magma coming up. Yes, there is wall friction. So but it may not be. It might be and not be a displacement term. It might be a velocity term. It might. I mean, it sticks slips, so maybe there is a displacement term there as well. There is. And I'm told, volcanologists tell me that as the magma is coming up a tube, it breaks off bits of the wall. So there's huge friction with the sides. It sets, so it's rock against rock, so it's like earthquakes. And we get swarms of earthquakes happening as these things are coming, as they come up.
I just thought that in the experiment case, it's slightly small. So I thought that the wall friction is very important. But the real case is very big scale.
Yeah.
So wall friction probably is very minor because of the scale difference.
Yeah. And yet, if you solve these problems without any wall friction, the maximum stress is at the bottom, according to these equations, when you work it out. So we really need to have something holding it down to get that. And that really makes a difference to where the maximum stress is. Yeah. Although those equations are quite complicated. I guess they were quite complicated. You know, when they're coupled, they're non-linear. There's a lot of them, and there's all the boundary conditions which I haven't even shown you yet. Right? So it's quite a complicated equation. But the process for dealing with this is to rescale, non-dimensionalize, choosing the appropriate scales. For me, that's the very difficult thing here, and it's the kind of thing that Fowler does all the time. So Fowler did that. He's very good at it. Choosing the appropriate, the length scale is easy, but the time scale should come out to be about a millisecond. We know that from the experiments, but you don't just put a millisecond in. You say, well, okay, he said, well, okay, it's the time scale for the gas to come out. Good. And so with a lot of care, you can choose the correct scale for your non-dimensionalizations. And then throw away small parameters. Anything that's a tenth or a hundredth or a thousandth, everything's all one except for these small parameters. Throw away the small parameters. Doing that simplifies the problem down to two key equations. We've kept one small parameter in here. The strain in the rock, there's actually a very small parameter here, the acceleration term on it. So we can see there's a wave equation here, in fact, and that's seismic waves. And so on small because they're very fast. But we've kept it in there for now. And we've got the pressure gradient driving stress, if you like. And this is how I think of it. The gas flow and the gas diffusion satisfies a non-linear diffusion equation. So ddt, and we've got one coordinate, z, vertical, and there's two derivatives in z. The diffusivity is depending on pressure, so it's non-linear. Gamma is about 1.4, it's the adiabatic constant. So we've got a non-linear gas diffusion equation, and then the pressure gradient arising from the flow of the gas creates stress. And yes, seismic waves too, but they're very fast, and we can throw away this term here. We're worried about it. We're worried about seismic waves. They happen very fast, a much faster time scale. Turned out we could relax about the seismic waves because the pressure at the surface actually on this time scale drops quite slowly, or it's not instantaneous drop. We've got a trace of how fast it drops, and it drops exponentially fast, but it drops. And then seismic waves, of course, occur immediately, and they happen very quickly. So they happen with very small pressure changes, and they just don't do anything. What is important is if 0 equals this, we then get related stress and strain, and we find R. The lambda, by the way, is the glue. With no lambda, you just get R. The rate of change of the divergence of W, the stress, is given by the pressure gradient. Yeah, of course, pressure gradient gives you stress. Where's the max? And then we ask where's the maximum pressure gradient. It turns out to be at the bottom, unless you have the lambda term in there. Then that modifies it. I should be a bit more careful about saying that. I want to get W subscript Z, dW dz, that's the stress. So I integrate this and I get pressure. So the pressure curve to leading order, if lambda is small, if there's no glue, for example, the pressure gives you the stress, just the pressure. It's changes in pressure, changes in stress. And the maximum pressure is at the bottom, so it predicts lift off from the bottom, always. But with the lambda in there, that modifies it slightly, just enough to give a maximum pressure nearer the top of the sample. So that was the magic ingredient in the modelling. First, the modelling was giving us these equations, and we were saying, oh, what's going on? It's not doing the right thing. You know, the nice simplification, but it's not expressing what we see. That's the other thing that impresses me about this. Coming down to these equations, you sort of say, how can you solve this? We don't need to. In some sense, we don't need to. We know what happens with the nonlinear diffusion equation. We know that pressure drops. Everything's, yes, you can't write down an equation for the formula of the pressure, but we've written down a very good equation for it right here. We know that it drops, and we can do some analysis of this equation, perhaps in asymptotics. But yeah, we know what happens. Just from knowing it's a nonlinear diffusion equation, we know that the pressure drops and goes through, and it drops on the time scale that we're talking about. So we've got the right time scale. So the non-dimensionalization that gave us this equation is almost more important than the equation itself. There's no parameters in here anymore. All the parameters are buried in the non-dimensionalization, so they give us t, we need z values. So very powerful technique. There are some parameters here. Beta is about 1. Lambda is the glue. It's of order 1. So almost no parameters left in the problem. All the parameters are in the non-dimensionalization. Very powerful. There is, though, yes, there's a parameter lambda. We did explore the dependence on lambda. There is one more parameter, and that's the rate of, it's the boundary condition, the rate of drop of pressure at the surface. It's very important. So yeah, okay, we've got this phi is porosity, W is the displacement of the rock vertically, gas pressure is P, and lambda is the glue, the wall friction glue, and time is just about up. So let's just move it along. So we have some boundary conditions. At the top we have a specified pressure drop with time. It's a shock tube, we drop the pressure. That's driving everything. Okay, and for that we need to look at the, and we need to worry about when does it break. We'll use some ideas from soil mechanics to give an effective stress, which is a combination of the total stress and the pressure, the pull pressure. And then they have a yield stress, which is the tensile strength modified by the porosity of the rock. And then we say, right, when the effective stress is greater than the yield stress, and this is greater than this, you can cancel out by 1 phi. People sigma is greater than sigma y. If we go to the non-dimensionalization, which we've been talking about, that becomes, we're interested in when W subscript Z, dW dz, is larger than this rescaled tensile strength. Rescaled on P0, P0 is the initial pressure, overpressure, 10 MPa. 1 minus phi is 1 minus porosity. So that's our criterion for breakage. The idea is to solve the equations, gas diffusion equation, solve it numerically perhaps, that's what I did, and when this criterion is met, break that bit of rock off, see where it's met, break it off, and now solve the problem of gas flow in the piece that's broken off separately to the piece that's still stuck, and do the kinematics as well. It's accelerating because it's pressure difference driving it. So do the forces mass times acceleration on the piece of rock as well, coupling all those together. It's a bit horrible, numerically, a bit messy, but not really amazingly difficult, like not like a 3D turbulence simulation. It's just you've got to couple some PDEs and some ODEs. That's all. So be careful. But as I said, there is one more parameter, and if you look at the pressure, here's pressure versus time measured from that experiment, and 3 probes. 1 probe is at the top, so here's the gas shock or the gas rarefaction wave coming down, meeting the sample, being modified a bit here because everything's breaking and lifting off, but basically dropping roughly exponentially. And here's the probe in the middle. Here's some broken bits going by, up and down, pressure going up and down, the bits are going by, and here's the bottom. Finally, it's broken off at the bottom as well, and the pressure there drops as well. So we've got that, and I want to use this to impose that as the surface boundary condition on my pressure diffusion equation. So that turns out, here's the data. So it's this curve here, and I've just digitised it, put an exponential through it. In the non-dimensional time, it's e to the minus 22t. So, and this 22 is a parameter, and it's the most important parameter. So then solve it numerically. I just use MATLAB. Gas diffusion is easy in MATLAB, PDE. But then I had this boundary value problem for the stress-strain relationship. I actually used a Green's function formalism for that. You could just do it directly as well. Given the solution of the gas diffusion equation, I can solve for W and then see if there's fragmentation. If there's fragmentation, use the kinematics, use forces mass times acceleration to move the things along. So solve all that together with small time steps. Not pretty, but it was effective. So yeah, we're solving 2 equations. We're solving this nonlinear gas diffusion equation, and we're solving this stress-strain relationship, which is it's a boundary value problem. We've got values at top and bottom. W and WZ are specified at the different ends, so that's where I use the Green's function there, but it's just a boundary value problem. And we have the beta's been set to 1, if you're worried about that. And then we've got to check for breakage by solving this and seeing what WZ is. Just do that every little time step and see. Breakage, okay, now remesh it, go again. So the result of that is to give me pictures like this, so I can give you pressure or density versus distance in at early time and then late time, so the pressure dropping, and then a bit breaking here, so the pressure there drops faster. And you see as this bit moves away, There's a constant pressure region in the gap between. There's still constant pressure in the gap between. So I'm not solving the flow of the gas at all in gaps, just the flow in the rock. And here's another bit broken off here, and it's moving away too. And this bit's glued in, and eventually a bit will break in here as well. So you see that. That's the pressure or the density, they're related, dropping. Here's that stress, the strain, stress. dWdz. Critical value for dWdz was about just below 0.06 for this particular setup. And we see at early time the stress rising, and there's a slight local maximum there. And then when it reaches the critical value, breaking here, and suddenly I'm dropping stress to 0 there, and then the stresses are rising again. They're rising because the gas flow is flowing faster and faster and applying more and more stress. So it works, and we get a length scale. There's the first breakage, and then the second breakage and third breakage. The length scale comes from that. We can look at a contour plot of density. Oh, actually, this is stress, dWdz, yes. Stress versus distance, and time's going this way. So initially, there's no stress, everything's blue, and the stress rises to red, and at the critical value, bang, it breaks there, and then we have two pieces, and the stress is rising, bang, it breaks there again, and this one, the stress is rising, bang, it breaks there again, bang, it breaks there again. So you can see the thing's breaking and accelerating away, so this is upwards. So Z here, time that way, and you can see the pieces breaking away. You can see the stresses in them, and stresses, some oscillation actually in the gaps and in the inside as well. The oscillations are because of the coupling between the acceleration of the pieces, and they accelerate, but then the bit in front of them is in the way, so the gas pressure goes up, so they wobble a bit. The kinematics is also a little bit complicated, but not so important. The main thing that's happening is diffusion and critical stress being there. So some quite nice numerical results. And yes, I can graph them too. We can see the stress going up and then breaking again. And then these bits moving across. And this bit here, there's not enough gas in it, it won't break again. And sometimes you don't know if the glued in piece will break or if the piece that's just broken will break, because the stresses are rising in both of them. And there's the pressures or the densities will drop in there as well. So it's possible to create movies from numerical simulations too. And from those numerical simulations, we get a picture like this, which looks, and all I've changed around is I've changed this tensile strength of the rock. Everything else is fixed. There's no free parameters here, except the tensile strength of the rock. Yeah, okay, maybe the permeability and the porosity. But the porosity, we know, the porosity, so it's fixed. So I just move the tensile strength around. They give you values for rock. There's a range. About 2 MPa, that's what I've used. And it's about what they think it is, that tensile strength. And we get pictures like this. So we're getting the primary fragmentation, getting the secondary fragmentation, we get tertiary and so on as well. And we're getting the fragmentation speed from there. So it's a pretty good result, I think. Yes, we can match those, and yes, we can match those, but they could too. So that's no big deal. Here's our results. Here's the other shock tube results. We have a jump here, and that I think is more physical. In their results, you have the fragmentation speed going to 0. But in fact, you can imagine you do an experiment with low pressure, nothing happens. So here we are here, low pressure, nothing happens, nothing happens, nothing happens. And then the rock breaks. Of course, by then, you're pulling hard enough that it breaks some distance in, so you get a finite speed. You don't get 0 speed in the limit. So that's why there's a jump. I think that's more physical than the shock tube results. It's time to conclude. I think we've got a nice match to experiment. We didn't have a lot of parameters to vary. It's not empirical. It's based on some physics, gas flow, porous medium. We can get those length scales. Our model is a solid rock with gas flow through it model, not an assumed fluid model. Good matches to the data. It's physically based. There's a bit of a step though. We're just working on experiments. Volcanic eruptions, that's something else again. You've got fluid rising. It's fluid. It's huge variation of viscosity. So it's sort of solid and fluid. It depends on the temperature and where you are. And then there's gas coming out of solution because of the pressure change. So it's a much more complicated situation to model than we've tried to model. So, but maybe upflowing magma might be a good challenge to try. We're in no hurry to do that because what's driving this part is we have good data. And to me, that applied mathematics, you can do the modelling, but you need good data to know you're doing the right thing. We were doing the modelling and we knew it wasn't right because we couldn't match the data. It was vital that we had good data. And I'm not sure, applying magma, that we've got much of this sort of data in there. We don't have a high-speed camera down there pointing at it, looking at what happens, So we're a bit limited, I think, maybe for data. And that, for me, that drives the modelling. If you only have good data and then you try and explain it with some modelling. I'm quite interested in applying this with colleagues at Massey University, colleagues of Bruce's actually, Tammy and her student Luke. They're interested in geothermal eruptions and they have some experimental data as well. So this model might be adapted to geothermal eruptions where this water turning to steam underground is the cause of the eruption. It's not the same, but the stress strain things are going to be the same, and maybe it's adaptable to, the ideas are adaptable to geothermal eruptions. Thank you. Time's up.
Is there any question?